Everyone. My name is Amanita Patel. Today we're going to be talking about the project that me and my teammates have built, which is Knowledge Graph for Intelligent Farming and Crop Monitoring. Next slide. Today we're going to be discussing about the interaction problem definition approach and high-level system design, ontology design, and how we're doing the reasoning, how we generated the queries, and we're going to be showing our live demo too. Next slide. Modern farming produces a lot of data like soil tests, yield history, weather, pest records. Most of this sits in different systems that don't connect or use the same terms. Because of that, it's hard to look at everything together and understand how soil, weather, and crop choices jointly affect yield or pest risk, or if we know when the fertilization is required. Knowledge graph lets us bring all this information into one connected model. We present plots, crops, soil, and weather as linked nodes and relationships, and use ontologies like OWL2 and SOSA, so everything follows a common structure and vocabulary. On top of that, we add rules to capture basic farming logic and query these results with SparkQL, exposing them through a simple Flask-based web application. Next slide. Right now, soil, yield, weather, and pest data are stored as separate silos with no shared meaning. Different formats and terms make it hard to combine data or reason across domains. So most tools focus on only one aspect at a time. So the problem we address is how to build a single reasoning-enabled framework that integrates soil, yield, weather, crop, and pest data into one consistent knowledge graph. By reusing ontologies like SOSA and adding rule-based inference, we aim to generate clear, explainable recommendations for crop rotation, fertilizer use, and pest risk mitigation. Next slide. Now, my teammate Ashwin will tell you how we approach this problem.
Okay, on to our approach. So our approach follows a structured semantic modeling pipeline combining ontology engineering, data processing, reasoning, and querying. We start with three datasets, which is yield, soil chemistry, and weather. And all these datasets are from 2011 to 2024. Since each dataset has a different structure and granularity, we pre-process them first. Soil and weather are site level annual context. Yield remains plot level. After pre-processing, we convert the cleaned CSVs into RDF triples. Each soil, weather, and yield record becomes a SOSA observation instance, and each observation links to a plot, a crop, and a year, and an appropriate measurement properties. We model everything using OWL2 aligned with SOSA ontology. SOSA gives us a consistent way to represent observations and features of interest across all datasets. Once the graph is populated, we apply swirl rules for reasoning. These rules operationalize agronomic knowledge. For example, if soil nutrients are low and weather predicts heavy rain, we postpone fertilizer. Or if a cereal crop was grown under depleted nutrients, we recommend legume next year. Finally, we expose the results through SparkQL queries. These queries retrieve inferred recommendations, combine soil weather yield relationships, and make them available for the application layer. Next slide. About our high-level system design, our architecture has 5 layers: data layer, ontology layer, reasoning layer, query layer, and application layer. Data layer is the raw CSVs. That's the soil chemistry, yield records, and daily weather data. Again, from 2011 to 2024, all clean and pre-processed, and we can merge them into one big dataset. Next is the ontology layer. This layer defines the classes we use. That's plot, crop, yield record, soil measurement, weather summary, and recommendation. So such structures the observation model. Each measurement is linked to a plot and a year. Reasoning layer. That's swirl rules encode agronomic logic such as crop rotation, fertilizer timing, and nutrient deficiency alerts. The OWL reasoner produces inferred triples, that is, new recommendations the system generates automatically. Next is the query layer, SparkQL. That's the same thing. Yeah, SparkQL retrieves both asserted and inferred information. This layer provides queries like next recommended crop, and then if fertilizer is needed or not. Lastly is the application layer. We use Flask API. We wrap the SparkQL queries so the front end can call endpoints to get recommendations. This allows integration with dashboards and visualizations without exposing the complexity of the knowledge graph. And now the next slide.
Hi, everyone. My name is Kavya, and I'll be taking you all through the ontology design, starting off with principles and classes. So as Arjun mentioned, our ontology is built in OWL2 and aligned with the SOSA ontology, which gives us a standard structure for modeling observations such as soil, yield, and weather. All measurements are modeled as SOSA-compatible observations linked to a plot, which serves as our feature of interest. We define a small set of core classes like plot, which is the field of experimental unit, then crop, which has subclasses like cereal crop and legume crop for rotation reasoning, and the record class, which is an abstract observation class with children, that is yield record, soil measurement, and weather summary. Lastly, we have the recommendation class, which gives the output class for reasoning, with the subclasses for crop rotation, fertilizer, and pest management. These classes give us a unified structure for representing soil, crop, yield, and climate data, so they can be reasoned over together. Next slide. Next, talking about the object and data type properties, our ontology is driven by a carefully designed set of properties that link observations together. Key object properties include about plot, which connects a record or a recommendation to its plot. For crop, links a record to the crop grown. Then uses soil measurement and uses weather summary. They allow recommendations to reference data. Lastly, recommends crop is used for crop rotation outputs. Data type properties store actual measured values such as soil pH, nitrogen, phosphorus, potassium, rainfall amounts, temperatures, and yield. These properties make it possible for swirl rules and SparkQL queries to use numeric thresholds and cross-domain conditions to infer meaningful recommendations. Next slide. Following up on the reasoning and query layer, the reasoning layer contains swirl rules that infer new knowledge. For example, if soil nitrogen is low and the previous crop was a cereal, a rule infers a crop rotation recommendation, suggesting that the next crop should be a legume. This approach encodes real agronomic heuristics into machine interpretable logic. SparkQL is then used to retrieve both raw and inferred facts, such as plots needing fertilizers, pest risk plots, or suggested new next crops. In our implementation, the OWL ontology and TTL instance data are loaded directly into an in-memory RDF-lib graph. All SparkQL queries run locally inside the Python application, and the Flask backend returns these results to the smart farming dashboard in real time. Next, we'll see the demo.
Okay. Hi, I'll take you over through, first I'll walk you through the code structure and then give you a quick demo of our UI of how the project is working on. So let me start off with what are the code structure looks like. So we have divided the code structure in a couple of folders, backend and the frontend. So where the backend folder has an data folder which consists of all of our data which we'll be working on. Secondly, we started building up the OWL file. So all of those data properties, the object properties and the classes which were explained previously in the previous slides, all of those have been implemented in this OWL files. We have added classes, we have added object properties defining their domain and range and every other thing. Now, once we were finalized with the OWL file, then we had used another Python script to generate the TTL file. So we have used a Python script to generate a TTL file which combines your OWL file and the CSV file to generate an instance.ttl file. So once our instance.ttl was generated, now it was time to write our SWRL rules and SparkQL query so that data could be fetched from those TTLs and the CSV files. So we have used this file called as queryservice.py file. So in this file, you would see all of those queries which we'll be using later in our UI have been used here. So for example, I could give you a brief overview of one of those queries. So let us walk through one of these, like find out whether a given plot is in high pesticide risk or not. So here we have only used two parameters, considering that if the rainfall is higher than 950 and if the yield is lesser, that is if the yield is lesser than 2500 kg per hectare, in those cases, yeah, this is a high pesticide risk plot. So we have added SparkQL queries over here, and with the help of, now once we have added all of these SparkQL queries, now we have used Flask APIs to expose these endpoints. So we have multiple endpoints. One is for whether the plots need fertilizers, whether it is a legume crop, a cereal crop, whether it's in high pesticide risk plot, and we have also added another endpoint of what would be the next crop recommendation for a given plot and a given year. So all of, at the end of this, we cover the backend part of our code structure. Similarly, now hovering around the front end part, the front end part is predominantly a React JavaScript file. So you would see most of our code has been written in been written in this file called as app.jsx. So where we have used a React plus Vibe connector to show all of the elements which we'll be fetching from our backend and showing it on the UI. So let me not go very deeply into this code structure and move on the UI part. So here is how the UI would look like of our recommender system. So before I explain you what what would the final recommendation be, let me walk you through what would be the plot. So a plot is a drop-down menu where you could choose the plot numbers, and here you could, as our data set consists of years from 2011 to 2024, you could choose any of those years. So once, for example, let me choose T2R4 or like T1R1 for the year 2014. So if I would choose T1R1, the plot T1 for the year 2014, it says that the crop cultivated during 2014 was a year and yield was around 8,000 kgs per hectare, with all of these values for soil and these values for the weather. So the soil contains elements like its pH value, the like potassium and phosphorus values. It also contains the weather information, such as what was the rainfall during that year and what was the average daytime and nighttime temperature during that year. So once you have selected your plot and year, we populate three recommendations below. So this first recommendation talks about needs fertilizer. So yeah, so we this plot, if you were to cultivate in 2015, you would need fertilizer for this plot. Yes, currently this is an high pesticide risk plot, and the next crop to be cultivated would be a legume crop. So these are the three recommendations which we provide from our rules and ontologies and TTL and our APIs. Now let me move back to the presentation of conclusion.
Yeah, so concluding the project, I would like to say that our work shows how semantic technologies can be integrated to a single interpretable decision support system for smart farming, unifying soil, yield, weather, and crop data with using an OWL2 and SOSA knowledge graphs and augmenting it with SWRL reasoning and SparkQL querying. We are able to convert and rather generate clear and explainable recommendations rather than having a black box output. I think using Flask API, which is really lightweight, it makes things insightful, accessible to external systems and data-driven supports for agronomic decisions. Overall, this approach illustrates how knowledge-centric models can bring transparency, consistency, and rather automation to intelligent farming workflows.